going to introduce material from chapter 7. This is still exam 4 material. And last week, we took a general look at chemical reactions, that is, writing chemical sentences and balancing equations. And today in chapter 7, we're going to expand upon that, but we'll actually narrow our focus. Chemical reactions only in aqueous solutions. I had mentioned, I hope I had mentioned earlier, that when you write a chemical reaction equation, you're nearly always given the reactants and the products, because it depends on the conditions of the reaction as to what the products are going to be. But this is one class of reactions in aqueous solutions. They're double replacement reactions. These reactions are ones in which all you need to know is the starting materials, the reactants in their aqueous solutions, and you can deduce what the products will be. So, and I've built in a buffer. This is Tuesday. Thursday is a buffer day. And if I don't finish today, then we have next Thursday as a buffer day. If I do finish today, then I'll pick up next Thursday. I'll start the review process. And the review may take more than one day. Let's get rolling on chapter 7. All right, those are topics. I always put those at the beginning just for clarity. Oh, I need to take this second. Hello? Okay, fine.
From CHEM100 gabapentin. Is she still taking this medication?
She had an older prescription, and she used up what was left. It seems to help with her restless leg sometimes, in addition to the.
I want to make sure before we fax this over.
Oh.
Don't take.
It's as needed. Yes.
I just want to make sure. Out of it or?
Yes, we've run out completely.
Okay, so I'll get this faxed over to CHEM1, okay?
Okay, appreciate it. Oh, but
yeah.
A question. I know she's got an appointment next week, but I don't have fixed to my refrigerator any lab work. Is this a visit, a follow-up with no lab work? You have. Okay. Yeah.
You'll probably do it this time around. That's what I thought we did last work, we did all this.
Okay.
Then you'll probably somebody order it on this visit.
Okay, so for the following visit?
Yes.
Okay, thank you. That's what I needed to know.
You're welcome.
Okay.
And I'll get this faxed over.
Appreciate it.
Thank you. Have a good day.
You too.
Bye.
Oh, sorry for the interruption. I'll cut that interruption out of the video when I process it. Back to our topics. Chemical reactions don't occur unless there's some advantage to the reaction itself. In other words, there's some benefit, chemical benefit to producing products from reactants. Otherwise, they won't react. And we categorize what drives the reaction as these, usually, not always, but usually one or more of these four driving forces. One is if in the process of adding two solutions together, this is typically the situation in which you find formation of a solid. If you put two solutions together and the reactants form an insoluble compound, we call it a precipitate. And that's a solid formed from addition of two solutions. That tends to drive the reaction forward. Think of it this way. When you put these two solutions together, right, and you combine the two solutions, and say they go into one container, then and these are typically ionic compounds in solution. And we're going to restrict our discussion here to aqueous solutions. When you put those together, then you get cations and anions available to interact that were not able to interact before. And if the formation of the compound, the cation plus the anion, has a very low solubility, or what we consider insoluble, then it will drop out as a solid. Well, when you do that, you're effectively removing ions from the reaction environment. So let's say we put, let's try sodium in aqueous solution plus chloride in aqueous solution. And that's one solution. Then we put that together with another solution that has silver in it. And this might be nitrate. So silver nitrate is completely soluble. We learned that last in chapter 6. But when you put them together, now they have the opportunity to interact. And the sodium combines with the nitrate. And we found that that compound is completely soluble. But the silver would combine with chloride. Solid. Right? So here are our products. Well, one law that governs chemical reactions, we'll get to it eventually, is called Le Chatelier's principle. And if you form a solid on this side, now these ions are no longer able to participate in the reaction. And we learn also that reactions can go forward and reverse. So the possibility that going reverse now, well, it's not possible anymore because we've taken these ions out of solution. So what it does is, in effect, drag the reaction toward products. That's what we mean by the driving force is a formation of a solid. Okay, the second one that's commonly seen is the formation of water. And this, not always, but typically this occurs with the reaction of an acid and a base. And an acid in aqueous solution plus a base in aqueous solution will yield a combination of hydrogen and hydroxyl, which is water. Okay. And the sodium chloride, which is completely soluble. This drives the reaction toward products. The reason for that, and we'll pick this up in more detail later, but the reason for that is water is it does dissociate into ions. It could go back because this is a combination of those two ions and this is these two ions. but it doesn't readily form hydrogen and hydroxyl ions from the water. Does just a little bit, but not much. So when we form this, that effectively takes the hydrogens and the hydroxyls out of the reaction mixture and does a similar thing to the precipitate. It just removes those from the reaction and drives it forward to the products. Transfer of electrons is another driving force. These are called oxidation reduction reactions. And I'll explain what this means in just a minute. But essentially, it's a transfer of electrons. Say if you put sodium together with chlorine, and you get a transfer. Metals prefer to lose electrons in a chemical reaction, and nonmetals tend to want to attract electrons. So if we transfer an electron from this sodium, and it's going to take two of them, so 2 electrons to this, then you get that product. The transfer of electrons is what drives the reaction because they are attracted to the chlorine and the sodium wants to give them up. Now there's an underlying structural explanation because of the way atoms are built. In other words, we know that sodium tends to form a +1 ion. Right? It's an alkaline metal. We learned that when we learned to name compounds. Chlorine tends to form a -1. Well, the reason they do that is because they complete their electronic structure that way. If sodium loses an electron, then it tends to look like neon. Okay. It isn't neon, but electronically it looks like neon. And these elements, when they react, tend toward an electronic configuration that is identical to, or we call it isoelectronic, to noble gases, because noble gases have a complete electronic configuration, and that's why they don't react. Chlorine, when you add an electron to chlorine, it tends to look like argon. So this transfer of electrons is preferred by the reactants, and that drives the reaction forward. And the fourth one that we want to introduce is a driving force, the formation of a gas. If we put zinc metal together with hydrochloric acid, the zinc with this actually transfers electrons too. The zinc will transfer an electron to hydrogen. And by doing that, it allows hydrogen to form the gas. Now the zinc, well, actually it transfers 2 electrons, but it forms zinc chloride. So we have 2 of these and 1 of those. Okay, so the formation of the gas in this case, we're saying is the driving force for a similar reason to the formation of a solid or water, because when we form a gas, it escapes the reaction mixture and pulls the reaction that direction. Okay, so these are the 4 primary driving forces for chemical change. And this, in fact, includes transfer of electrons as well. So you've got the formation of a gas, you got the transfer of electrons, causing that reaction to proceed to products. Oh, okay, I've got a I've got a little video here and just get it started. It's self-explanatory.
So in the reactions we've seen so far then, we mix chemicals together and we know that a reaction has taken place because we get a change of colour. But there are lots of other ways that a chemical reaction can show up. And one way is called a change of state. So the state of something just means whether it's a solid or liquid or gas. So if something turns from a solid to a liquid or from a gas to a solid, then it's changed state. So let me show you an example of a chemical reaction that involves a change of state. So I'm going to use these two liquids. I have a red liquid and a colourless liquid. What I'm going to do is to pour the colourless liquid onto the red liquid very carefully and try to make two layers. So what I want to happen is for the colourless liquid to be floating on top of the red liquid in separate layers so that they don't mix. Okay, so I think that's worked quite well. So what I've got now is one liquid floating on top of another, and where they meet, they undergo a chemical reaction. And they're actually making a solid. A solid material is formed where the two liquids meet. And what I can do is to fetch out some of this solid material. And as I pull it out of the beaker, of course, it allows the two liquids to meet each other again, and so they react again to form more of this solid. So if I'm careful, so as I wind, I'm pulling up this material and it allows the two liquids to meet again and it forms more of this material. And this substance that's being formed is actually nylon. So we're making nylon as I speak. And if I'm careful, I'd be able to just keep on turning this and making this long thread of nylon, at least until we run out of solutions. Okay, so that's an example then of a chemical reaction that involves a change of state. So let's have a look at another reaction that involves a change of state. And for this, I'd like a volunteer, please. Who would like to volunteer? You're very keen. Come on down. Let's have a big hand for a volunteer. You would like to stand there. Let's pop those on. What's your name?
Dylan.
Dylan. All right, Dylan, if you stand just there, we're going to do some chemistry and we're going to make it a solid. All right, I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. Now when I add the ammonia, you see that it's forming a sort of brown colour. I'm going to keep on adding the ammonia, and in a minute that brown colour should disappear. There, it's disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So I'm now going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. This takes a moment or two. There we go. And then finally, I'm going to add some glucose. So there's the glucose. Now I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan, and I want you to hold that, and I want you to give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place, and it's forming a solid. And the actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour, is that okay? It does actually take a minute or two, but the harder you shake, the better it works, so keep shaking. Don't drop it, though. Okay. So metal, silver metal is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal in the form of a mirror building up on the inside of the flask. And you're all seeing those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. The little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, let's have a quick look. Almost there. Keep going a little bit longer. Still looking a little bit dark. Excellent. All right, give it back to me then. Right, so I'm going to take the clip off. Take out the stopper, just wash that off. And I'm going to pour out the remaining chemicals. And then I'm going to rinse this out with distilled water. I'm going to rinse it out a second time. Rinse it out a third time. There we go. And just going to put that on, just dry this off. And put the clip back on. And if you'd like to just give that a little polish. There we go. If you'd like to hold it up by the neck, that's it. And if we bring a camera in and have a look at this, and we've got a lovely silver mirror. There we go. I'll just stand there. Okay, what I'm going to do is give that to you as a souvenir to take home, and you can go back to your seat. Let's have a hand for our volunteer. Okay, so that's an example of a chemical reaction that produces a change of state. I want to show you another example of a chemical reaction. Again, this is going to go from being a liquid to being a solid. So in this flask, I have a solution of sodium acetate. And this sodium acetate's a liquid, as you can see, but it would very much like to be a solid. It would like to turn into a crystal. But it needs a sort of an excuse to get going. And the excuse is going to be some little crystals of solid sodium acetate in this dish. So watch what happens as I pour the liquid onto the crystals. So I think you can see there the liquid, as soon as it touches the crystals, is turning into a solid. And with a bit of luck, we can make a sort of chemical sculpture. Seems to be working. Okay, so that's a sort of sodium acetate sculpture. Now, oddly enough, this actually has a practical application, and this is the practical application. This is something called a hand warmer, and it's a plastic pouch, and it contains exactly the same liquid as in this flask. It's a solution of sodium acetate, and it would like to turn into a solid, it would like to turn into a crystal, but it needs an excuse to get going. And the excuse is this little metal disc, and if I just flip this disc backwards and forwards, that should be enough just to start the crystallization off, and there it is. And we can see the liquid turning into a solid. And as it does so, it's actually getting warm. So it's actually giving off heat. And there it is, it's turned entirely into crystals. It's become quite warm in the process. I can put that inside my glove and keep my hands warm for half an hour or so. And then I can take this and put it into boiling water for a couple of minutes. The crystals will turn back into a liquid. I can allow it to cool, and they'll stay as a liquid. It'll stay like that for weeks or months until I'm ready to use it again. I can use it thousands of times. Okay, so that's sodium acetate, a sort of chemical sculpture. I'm going to show you now another way to make a chemical sculpture. And Chris has been preparing this. This beaker contains a mixture of para-nitroacetanilide and sulfuric acid. And Chris has been warming it up. And when it's hot enough, it will undergo a reaction in which this liquid will turn into a solid. This makes quite a bit of smoke, so we've got this special hood that will suck away the smoke from the reaction. Okay, here it goes. Okay, so that's a chemical reaction that involves a change of state.
All right. So let's go to the next slide. All right. So this video actually goes on and on and on, and it covers a whole range of different types of chemical reactions. I thought I'd give you just a taste of the reaction which forms a solid. This is another, we discussed this earlier, the precipitation reaction forms a solid when two solutions are combined. And here's another video that actually demonstrates this. Sometimes it's hard to hear, so we have to, I think I've got the sound turned up as high as it'll go, and we just have to be quiet and listen.
What I have here is two Erlenmeyer flasks. One has lead nitrate solids in the bottom, and one has potassium iodide solid or salts on the bottom. I'm going to make solution, an aqueous solution with these. So I'm going to make aqueous lead nitrate here. Mixing, you can see that it makes a solution. And it does dissolve. It is definitely aqueous. And same thing with the potassium iodide. Hopefully I don't make as much of a mess. This is the Ki, adding some water. Also making an aqueous solution. And both of these solutions, or both of these salts, are soluble in water. So as I stir, and I have two aqueous solutions. You can see through them, and you can see the solids are now been dissolved. Okay. Now, interesting enough, lead nitrate is made of the nitrate ion. The nitrate ion is NO3 - 1, and anything combined with a nitrate ion is soluble because the nitrate ion, NO3, is 4 atoms stretched, and you have a -1 stretched over 4 atoms, so its charge density is very low, so it doesn't attract other ions in a crystal as strong as others. So its lattice energy is lower, and it's easy for water to pull apart the ion and have those molecule ion attractions that make this a possibility. Same thing with Ki. You have potassium iodide, and you have Ki ions that are free in this aqueous solution, and the K is +1. The +1 ions are a big ion, and they are spectators for most types of reactions because they have a +1 over a large area as well. And the iodine, like most halides, are also soluble because they're a -1 and they're also a big ion. There's some exceptions with those, and we're going to see that one right here. So I'm going to pour these together and take two aqueous solutions and see if a precipitate results. Now, precipitate is when a solid comes out of the solution because we're going to do a double replacement, or something called a metathesis reaction. Lead +2 from this beaker is going to attract and hook up with the iodine ion to make PbI2, or lead-2 iodide. And that is going to create a precipitate because the lead iodine prefers itself more, or attracts itself more, than water. So let's do that. Here we go. Very brilliant reaction. And you see that as pretty, very pretty yellow precipitates. A lot of yellow lead paints have been known to be yellow, and also a problem. So there you go, and there's your precipitate. And it's a precipitate because I know that I cannot see through the solution anymore. And if we let this settle for a while, we'll get something like this. This is a reaction I did about an hour or so ago, and you can see here that the clear solution is the potassium nitrate ions, or the potassium and nitrate ions, and the solids are at the bottom. That's settled at the bottom. All right? So there is your precipitating reaction.
Okay. So while he was demonstrating that experiment, I was putting the reaction on the board that describes it and then balancing it, of course. And this is what we call the molecular equation or the formula equation. This is actually what's happening when we combine the two solutions. The lead ions and the iodide ions combine to form a solid. And the nitrate and the potassium ions remain in solution. They're what we call spectators. All right. Okay. Now let's talk about aqueous solutions and some of the things that describe an aqueous solution and make aqueous solutions common. Water is often described as the universal solvent. Now that's a stretch because there are some things that are not soluble in water, like our example in that previous video. And other things like oils are not soluble in water. And there's a reason for that I hope we'll cover in a few minutes. But water does dissolve a large portion of elements and compounds that we find in nature. Water is a polar molecule. What do we mean by polar? Well, think of a magnet. Right? We know magnets have a north pole and a south pole. And if they come close to another magnet, they tend to orient themselves so that the south pole attracts the north pole and the north pole attracts the south pole, the other one. Molecules are polar in a slightly different way. This is magnetism. Molecules tend to have an uneven distribution of electron density in their makeup. So if we have a water molecule, which is one oxygen, and then two hydrogens bound to that oxygen, each element has its own strength of attraction for electrons. And in covalent bonds, right? So oxygen has a tendency to draw electrons to itself more strongly than hydrogen does. Now, it's not strong enough to completely remove the electrons so that we have an ion, right? But since these are both nonmetals, we get a covalent bond. They're sharing electrons, but they're not sharing equally. We have a tendency to concentrate electron density around the oxygen, and that makes the hydrogens deficient. Okay, so overall, what that gives us for the molecule is a negative side and a positive side. That's the nature of a polar molecule. And water is a very strongly polar molecule. So what it does, and this describes the reason that water is a polar molecule. It's bent. If water were straight like this, then we would have attraction this way, but the polarity would balance. So it would be considered a non-polar molecule. But since it's bent, we get a concentration of positives on this side and negative on that side. Okay. Polarity of water makes it a very good solvent for ionic compounds, where you would have, say, sodium would be attracted to this side, right? And the chloride would be attracted to this side. right? Or if you have other polar molecules, they don't have to be ions, but if they are polar, then they orient themselves so that their negative side attracts to this side and their positive side would be attracted to that side. And that helps bring them into solution, keep them in solution. Of course, with those exceptions where we find the strength of attraction between cations and anions is stronger than it is for the water molecule, then you form the solid and they drop out. But large numbers of compounds and elements are water soluble. And they go through a process called hydration. Where the cation is surrounded by water molecules and the anion is surrounded by water molecules, orienting themselves so that the positives and negatives attract. And that keeps them in solution. Okay, here's an animation for that. So we have this sodium chloride crystal, and it's going to be attacked by water molecules. Right? And they have the strength of attraction is such that it's not just these 4 water molecules. They tend to orient themselves, but now they have, and that's actually, this one on the left-hand side is oriented improperly because it's got positive against positive. So that's an error in the animation. But the ion is surrounded by water molecules, but those water molecules are still being pulled by other water molecules on the outside of the crystal. And that force of attraction of those other water molecules pulling eventually dislodges the ions from the crystal and puts them in solution. And that takes energy. Okay, so the chloride ion is also attracted. Okay, I think that one, we got that one right. The positive side's attracted to the negative, and it just continues. Now, once they're dissolved in water, those ions now, if we consider sodium chloride in its solid form, so we have an array of cations and anions, and it just goes on and on and on forever, well, to the size of the crystal. Those ions are locked in position in this solid. So if you put a battery, right, on this side, contacting that crystal, and you put the other one on this side, and say you put a light bulb in between. So we have a light bulb in between, that bulb will not light because sodium chloride solid is an insulator. It does not conduct electricity. Why? Because the ions can't move. They're in a solid crystal lattice that holds them in place. But if we put them in solution, now those ions are free to move. And if we apply a charge on either side, we'll get that. If this now is in aqueous form, then we'll get those ions, they're able to move and they can transmit a charge and complete the circuit. Okay. When that happens, this is an operational definition. If you put anything in solution, and then it is consequently able to conduct an electric charge, then it's called an electrolyte. If the dissolution is complete, if the compound is very soluble in water and forms these ions, then we call it a strong electrolyte. Sodium chloride would be an example. Hydrogen chloride or hydrochloric acid would be an example. Strong acids do that. They form electrolytes, which can transmit, can complete a circuit. While we're on the topic, if you have something that only ionizes a little bit, like acetic acid, vinegar, then it's going to provide only a few ions in solution to complete the circuit. So it doesn't give you a lot of current. So you have a weak light bulb. Those are weak electrolytes. Then if you put something in solution that does not dissociate into ions, like table sugar, sucrose, it readily goes into solution, but it does not break apart into ions. So it will not conduct electricity. That's a non-electrolyte. Okay. All right. So what happens when these two compounds are combined? Well, if they're in aqueous solution, then what actually happens is the ions separate. So we have potassium ions and chromate ions in one solution. We have barium ions and nitrate ions in the other solution. And they're surrounded by water molecules, keeps them in solution. But when we combine them, now these ions are free to interact, and the chromate and the barium ions combine to form a solid. All right. What are the possible products? Well, what we've done here is created a box with anions on the top and cations down the left, and all combinations are possible. So potassium nitrate, we say, okay, potassium combines with nitrate, is that soluble? So we look at our solubility chart. Our solubility chart, which is located in the review document here. And we look for potassium across the top here and the anions down the left, and we find potassium nitrate has a clear box, which means it's soluble. Same thing for potassium and chromate. That is also soluble. But when we combine barium and nitrate, we look for that one. Well, that one's soluble too. But when we look at barium and chromate here, we find a gray box that's insoluble. All right, and that's the decision process. In the event, if the ionic compound is in solution, then it must be separate ions. Then when you combine the ions, you get the possibility for cations from one solution to react with the anions of the other solution. And then you see what possible formations you can get. Now, potassium nitrate is a white solid if it's dry. But in solution, they're separate ions. Barium chromate, though, is a yellow solid in the environment, the reaction environment. It forms the barium chromate solid, which eventually settles out and collects on the bottom. Okay. These are the general rules for solubility, and these rules are used to generate that solubility chart. Okay. Now, if you were chemistry majors, you would memorize these rules. Right? But since you're not chemistry majors, I think it's just sufficient for you to learn how to use this chart. And like I showed you before, the cations across the top, anions down the left, and it's kind of like the old-fashioned road maps, where you have a city here and a city here, and you go where they cross, and it tells you how far they are on the road between the two. Well, here we get an interaction, and we see whether it's a clear box or a gray box. Gray box indicates insolubility, formation of a solid. Now, there's some exceptions to that where you have, and there are comments below, where the reaction may form something that's not stable. So you get a secondary reaction, and that complicates things. All right. Now, I will say this. Let's go back. These solubility rules, if you really want to learn them, the solubility rules are set up so that the number one is the highest priority. Then secondary, tertiary, quaternary, and on down are less priority, which means that if you have two rules that are applied to your reaction, the one above takes precedence. All right, so now we can continue. This is just another arrangement of the rules. For our purposes now in this course, since it's an introductory course, we draw a distinction between soluble. Let me make some room here. Between soluble compounds and insoluble. Okay. But the reality is that these insoluble compounds may be somewhere on this continuum. Instead of way over here, they might be over here somewhere. They might be slightly soluble. But for our purposes, we make a distinction between the two. They're either soluble or insoluble. If you took the general chemistry class, we would learn how to predict the solubility of compounds that were only slightly soluble. But at this point, we treat them one or the other. And for practical purposes, sometimes that's good enough. If you're trying to separate metals from a mixture of metals, and you add a solution with an anion in there that forms insoluble compounds with some of the metals, then you can start separating them. Right? Once they settle out, you can decant the liquid off and recover the solid, or you can pour it through a filter and recover the solid. And that will effectively separate most of the metals. And there's a sequence of steps that you can use to effectively separate most metals in a solution, in a mixture. So prediction of these, this is the type of reaction, this double replacement reaction, where we can predict the outcome. What you have to do is recognize that those soluble compounds are actually cation, anion, cation, anion. Then when you put them together, you have the opportunity to swap partners. In other words, the cation from one reacts with the anion from the other, and vice versa. And you then just have to ask yourself the question and use your chart to see which one is insoluble. If the reaction does not form an insoluble compound, then there effectively is no reaction. You just have a physical mixture of the ions. So that an example of that would be potassium chloride plus sodium nitrate. Right? The potential combination there would be potassium nitrate and sodium chloride. Well, if this is aqueous, this is aqueous, this is aqueous, and this is aqueous. They're all spectators. No reaction has occurred. So if there's a solid formed, then you can predict an outcome. All right. So let's clear the board. Okay. So here's a check on whether you're understanding the concepts that we've introduced. Which of the following ions form compounds with lead that are generally soluble in water? Okay, so here are our possibilities. Okay. Notice that we threw a twist into the last one, sodium ions. Sodium ions and lead ions don't form compounds because they're both cations. But we can look at A through D and check our chart to see if there are any insoluble compounds in there. We find that lead sulfide, right? Get our chart here, and we look for lead, which is way over here, and then we go down to sulfide. It's insoluble. Lead chloride, right? Lead chloride is insoluble. Okay. Lead nitrate is soluble. I know that because all nitrates are soluble. Lead sulfate is also insoluble. So the only soluble one in that bunch is the nitrate. Okay. Moving on. So if we have a sodium phosphate solution and we combine it with a solution of lead 2 nitrate, what precipitate will form? So here's where we go back to nomenclature. Sodium phosphate, you must be able to write the compound. Sodium, and then phosphate is a polyatomic ion with a 3- charge. Sodium always forms a +1 charge. So in order to balance the charges, we need 3 sodiums. So there's our sodium phosphate. And the problem tells us that it's a solution. So we say it's an aqueous solution. The second solution is lead 2 nitrate. This is a type 2 compound. So we know from the name that this is a 2+ charge. And it's combined with nitrate, which is a 1- charge. So that means we need 2 of those. Okay. So what's actually in solution? In solution, we have 3 sodiums for every 1 phosphate. And 1 lead, 2+ in solution, plus 2 nitrates. That's actually in solution. So now we can say, all right, sodium combines with nitrate. Oops. Nitrate. And we find that this is a soluble compound. So it's still in ionic form, the sodiums and the nitrates. I haven't balanced this equation yet. So what's left? Well, this cation and that anion can combine. Lead, phosphate. If this is a 2+ and this is a 3-, how do we reconcile those charges to make them balance? Cross multiply. 3 comes over here, and the 2 goes over there. And we look at our solubility chart, and we find that this is a solid. Okay? So that's the precipitate that forms from this reaction. Right there. All right. let's see, let's go ahead and balance this equation. We have 3 leads over there, but 3 leads here. That means 6 nitrates. So 6 nitrates. And we have, now we have 6 sodiums, so we need 2 here to give us 6 sodiums. That gives us 2 phosphates, which we have. So now this is balanced. Now this part is not balanced anymore because I changed the conditions. Okay, another concept check. A solution with the following ions present. Nitrates, that's your anion. The other anions are chloride, sulfate, and phosphate. Then you have the cations, the metals, lead 2, potassium, silver. So what's the question? When all are allowed to react, how many different solids will be formed? So here's what you do. You set up your grid. Right? We're going to set up this grid like it is in the solubility chart. So the cations are across the top. So we go lead 2 plus. Then we have potassium and then silver. Okay. And then down the left-hand side, we have nitrates, followed by chloride, sulfate, and phosphate. Yeah. Okay. Now we have our grid set up. That's kind of lopsided, isn't it? I can do better than that. There we go. That, here. Okay, so now we combine our cations with our anions. All the nitrates are soluble. So this is soluble, soluble, soluble. How about chlorides? Well, we look in our solubility chart and we find that silver chloride is insoluble. Potassium chloride is soluble. Lead 2 chloride, let's look that one up. So there's lead and there's chloride and it's insoluble. Okay, so we have insoluble here, insoluble there. Then the sulfate, we find that's also insoluble for lead. But potassium sulfate is soluble. Silver sulfate. Silver, here it is. It's also insoluble. Okay. Then lead 2 phosphate, we know that one, I think, from previous experience, is insoluble. Potassium phosphate is soluble. And silver phosphate should be insoluble. Yes. Okay. So we have 6 possible compounds that are insoluble. How many different solids? You have 6. And there they are. The leads, except for the nitrate, all the lead compounds in this list are soluble, and all the silver compounds are soluble except for the nitrate. So that tells you if you want to get lead or silver into solution for a reaction to occur, nitrate's a good choice. Silver nitrate, lead nitrate would be a good choice for the soluble form. Okay. I've been using an example of molecular equation followed by ionic equation. Molecular equation or formula equation, because ionic compounds are not molecular. Ionic compounds are represented by a formula, which is the smallest whole number ratio of cations to anions. But we still call it a molecular equation. That name kind of stuck. Just to be consistent. This is a molecule, covalent compound. That's not a molecule. Okay. All right. So the molecular equation simply takes the formulas of each of the compounds and keeps them separate as reactants and products. Our example here is potassium chromate plus barium nitrate solutions produce barium chromate solid precipitate and potassium nitrate in solution. That's a complete equation, a complete formula equation. Okay. However, this doesn't give you a clear picture of what's actually happening at the microscopic level. So what we do is we separate the ions into a complete ionic equation. And once you've balanced the formula equation, then you can take the subscripts out of that equation. For instance, K2CrO4, K2CrO4, like that, would actually be 2 potassiums, right? This subscript becomes a coefficient and 1 chromate in aqueous solution. Okay, that's what we're doing here with a complete ionic equation. Once we have balanced the formula equation, then we can separate out the ions in the same ratios as they were in the formula equation. And then barium nitrate would do the same thing. Then we determine which is the solid, which comes from the formula equation. And that stays intact as the solid. But the other ions now are available on the opposite side. And this is known as the complete ionic equation. This has everything that's in the reaction vessel. All right. Now, since potassium and nitrate are the same on both sides, we call those spectators, and we can cancel them to focus on the reaction species, those things that are actually driving the reaction. And if we exclude the spectator ions, now we produce the net ionic equation. So in our case, we would exclude this one, and the barium nitrate from this part of the equation would give us barium, and it would combine here to make barium chromate. Oops. My mistake. This is a 2 minus. And this is the solid. So these 2 ions are reactants. This is the product. This is the net ionic equation. Now, why would we go to all that trouble? Well, for some reactions, especially when you are investigating more complex reactions, and you have a lot of ions floating around that are not participating in the reaction, the formation of solids, it can get pretty busy. So if we eliminate the ions that are same on both sides, we can simplify the reaction so it's easier to visualize. Also, if we have say we don't have any potassium chromate in our lab, right? We're just out, right? But we do have sodium chromate. Okay. We get the same net ionic equation. We can form this solid from that compound and this compound just as easily. So that is, as a practical matter, you can work with what you have in your lab if you understand the concept of net ionic equations. All right. So here's another concept check, and we're gonna write out and balance the equation. For the molecular equation or the formula equation, the complete ionic equation, and the net ionic equation. So what are our reactants? Cobalt 2 chloride. So we have cobalt, and it has a 2+ charge with chloride. So we need 2 of these. Okay. And then we're going to combine that with sodium hydroxide. All right. So we need to know the products before we can balance the equation. So this cation can react with that anion and make sodium chloride. Except that's still soluble. So we got a bead on spectator ions right now. Then if we combine cobalt and hydroxide, we check our chart and we find that this is insoluble. Okay. So now all we need to do is balance the equation. One thing about these double replacement reactions where we form a precipitate from 2 solutions, they're relatively easy to balance. So we don't always need to use the budget. You can use the budget. Go ahead and use the budget if you want. But we need 2 chlorides on this side. Now we need 2 sodiums on this side. And we need 2 hydroxides over there and 1 cobalt. That's balanced. Okay. Once you get the balanced molecular equation, then you can separate out the ions. So we have a cobalt 2+ in an aqueous solution. We have 2 chlorides in aqueous solution. We have 2 sodiums in aqueous solution. And we have 2 hydroxyls in aqueous solution. On this side, we still have 2 sodiums and 2 chlorides, but we also have 1 cobalt 2 hydroxide solid. There's your complete ionic equation. Okay, molecular equation. See if I got that one. Yep. Okay. Then the complete ionic equation. There you go. Now, how do we do the net ionic equation? We look for spectators. We've got sodiums on both sides. 2 sodiums here, 2 sodiums here. We also have chlorides. 2 chlorides on this side, 2 chlorides there. So the net ionic is simply cobalt plus hydroxyl yields COOH2 solid. So there's your net ionic equation. Now, once you produce the net ionic equation, to carefully look at it to see, can it be simplified any further? In other words, if we had run through this whole thing and come out with 2, 4, 2, then we divide the whole thing through by 2 to reduce it to the simplest whole number ratio to 1, 2, 1. So you're not finished with a net ionic equation until you're sure that you have the simplest whole number ratio of coefficients. Okay. Now we're going to talk about acids and bases a little bit. Excuse me. And we don't have time for a complete discussion of acids and bases. But, well, let me see. Let me not steal my own thunder. Okay. We are going to restrict our discussion of acids and bases to this type of acid and base, the Arrhenius. Acid and base. There are other concepts for acids and bases that are more useful and cover more reactions. But since this is a survey course, it's an introductory course, we're going to restrict ourselves to this definition. An Arrhenius acid is a compound which, while in solution, produces hydrogen ions, plus some anion go with it. But it produces not free, but hydrogen ions, which actually combine with water molecules. But before we put, for example, this one, if this is a gas, this is hydrogen chloride. And we talked about this a little bit when we were learning to name compounds. But when you put it in solution, aqueous solution, now it's hydrochloric acid. And it's based upon the ability to dissociate hydrogen ions from the molecule. Whereas the base, an Arrhenius base, produces hydroxyls in solution. Okay. That defines an Arrhenius base. Now, if the compound completely dissociates, like hydrogen chloride, hydrogen nitrate, hydrogen sulfate, in solution would be hydrochloric acid, nitric acid, sulfuric acid. Those completely dissociate. They are strong acids by chemical definition. Okay. And this is a process of ionization. A bond has to be broken between the hydrogen atom and the rest of the molecule. Okay. So there's what happens when we put hydrogen chloride in water and make hydrochloric acid. It's also a strong electrolyte because this complete dissociation, this ionization, whereas the base is already ionic form. This is a plus and this is a minus. So all that's required here is for that, when you put it in water, it has to dissociate. But these are strong electrolytes also. These are strong bases. They completely dissociate in aqueous solution, and they are strong electrolytes. Now, what happens when you combine the two? Okay, let's clear the board. Arrhenius acid and base reaction. Okay, so what are the products? Well, let's take an example. Say you have sodium hydroxide in aqueous solution. You combine that with hydrochloric acid, and you get a double replacement. The hydrogen is attracted to the hydroxyl, and we form water. And then the sodium and the chloride are still in solution. Right? So this would be, let's see, we need two of these, two of those, and two of these. Notice that this would be a complete molecular equation, formula equation. And when a base, an Arrhenius base reacts with an Arrhenius acid, it always produces water and a salt. And that's salt in chemical terms. Table salt is sodium chloride, so that's a salt and it's table salt. But in chemical terms, combination of the cation and anion from the acid and base is a salt. And it could be anything. It could be calcium chloride. It could be potassium bromide, depending on the acid and the base that you use. Now, what's the net ionic equation? Well, if this is going to be sodium hydroxyl, hydrogen, chloride, this is water, this is sodium and chloride. Two here, two here, two here, two here, one there, two here, and two there. The spectators are sodium chloride that make up the salt. So the net equation actually I think there's a problem with the balancing here. So let's go back. With this water, I need two hydrogens over here. Okay, two hydrogens, two chlorides, two sodiums, two hydroxyls, two hydrogens. Well, that just means we can do this, right? One chloride, one sodium. Yeah, that's balanced, right? I went overboard. So that. Okay. So now we have this, these two ions form this water molecule. These are spectators. So the net ionic equation for an Arrhenius acid-base reaction is always hydrogen ion plus hydroxyl ion yields water. That's the net ionic equation for an acid-base reaction. Okay, common strong acids we mentioned. They completely ionize in water. Strong bases completely dissociate into the cation and the hydroxyl. And then the net equation for a strong acid and strong base is always, well, actually, a net reaction for any Arrhenius acid base is hydrogen ions plus hydroxyl ions yield water. Okay. Let's see. The net ionic equation for this reaction, we don't even have to draw that one. Hydrogen plus hydroxyl yields water. There it is. Okay. That's acid-base reactions where they produce water. And water, as we learned earlier, the formation of water is the driving force for an acid-base reaction. Now we're going to look at oxidation reduction reactions. For an oxidation reduction reaction to occur, electrons must be transferred. So that implies that some reactions don't transfer electrons. And our examples for the formation of precipitate, electrons were not transferred in those reactions. We simply just swapped partners. Cations and anions traded places, and we formed a solid. But if electrons are transferred, then we have an oxidation reduction reaction. Let's see. Okay. How do you know the difference between oxidation and reduction? Well, I don't think I have a slide on this one, so I'm going to put it on the board. We use this mnemonic device. Oil rig. This means that oxidation is loss of electrons. Reduction is gain of electrons, one or more electrons. So oil rig will tell you that oxidation is loss, reduction is gain, and they always occur together in a chemical reaction. If something is oxidized, something has to be reduced. The electrons don't just float around in chemical reactions, they don't float around free. That's physics. You can separate electrons out. You can separate ions in physical experiments, but in chemistry, we want balance. So whenever an oxidation occurs, a reduction occurs simultaneously. And the example here is magnesium metal plus oxygen gas. So if let's see, do we have the reaction? When metals and nonmetals combine, they always transfer electrons. There's your reaction. 2 magnesium atoms plus 1 oxygen molecule produces 2 magnesium oxide units formula for the solid. And notice that magnesium, when you start, has no charge, right? Electrons, it's complete. All of its electrons are there equal to the number of protons. So this magnesium would be 12, right? So we'd have 12 electrons. Okay, for each one. For oxygen is 8. So it has 8 electrons for each oxygen atom. But when we combine them and we get magnesium 2+ and oxygen 2-, okay, what has happened? In order to go from 0 to 2+, we have to lose 2 electrons. So now we only have 10 electrons, right? Because we have 12 protons, 12 pluses and 10 minuses makes 2+. And then oxygen goes from 8 to 10. Now each oxygen has 2 extra electrons. It has 8 protons, 8 positives, 10 negatives makes a 2-. So in electronic terms, these ions look like neon because neon has 10 electrons. Okay? That's the driving force, the tendency toward noble gas configurations. Okay, our example here is, let's see, aluminum plus iron 3 oxide. So we have aluminum and iron 3 oxide. These are both solids. That's what we're demonstrating there. On the left-hand side is this. And we start off with 0 here and 3- there. Right? Okay, so what happens is electrons are transferred from this aluminum, and we need 2 of them to be balanced. 2 aluminums take 3 electrons each. So 3 electrons are transferred over here. And what that makes is iron metal plus aluminum oxide. Okay? So for each one of these irons over here, we have, let's see, 26 with a 3, 3+ and 2-. These 3 neutralize that to make this neutral. And over here, though, it starts off at 23 electrons. So if we add 6 electrons, actually. Yeah, we need 6 electrons for 2 irons. So 6 electrons will make this one look like krypton. Okay. So which of the following best describes what's happening here? Well, the aluminum loses 3 electrons. So it's either C or D. And the iron gains 3 electrons for each atom. So for a total of 6. So D would be your best description. Now this particular reaction, this is called thermite. It's used a lot of places, but I know it's used for constructing rails for trains. 2 rails will be brought together and then a mixture of aluminum and iron with an ignition device inside is packed around it, and then it's covered to protect protect people from the heat and the sparks that come off of it, because it's a violent, highly exothermic reaction, lots of heat. But what it does is it forms iron metal, and it essentially welds those rails together better than the rest of the rail. If a rail were to break, the rail itself would break before the weld breaks. It's that strong. Okay, so oxidation reduction reactions typically occur between metals and nonmetals. Not always, but that's one way. Well, two metals, you can have an oxidation reduction reaction. You can have a metal and a non-metal undergo an oxidation reduction reaction. And you can have two non-metals undergo oxidation reduction. Okay, driving forces we've studied: form a solid, form water, transfer electrons, formation of a gas. Here's a precipitation reaction when you form two solids, double displacement. And there's a generic form. Okay, acid-base reactions. There's the net reaction. There's a molecular reaction that could be the net. Oxidation reductions transfer electrons. In this case, we're transferring electrons from a metal to a non-metal, from lithium to fluorine, and we form the lithium fluoride compound. This one's the formation of a gas. And let's see, we're done with that. I showed you this one earlier. Zinc plus hydrochloric acid makes hydrogen gas and zinc chloride. It could be considered it's an oxidation reduction reaction, definitely. Zinc has a 0 charge reactant, and as a product in zinc chloride, it has a 2+ charge. So it had to lose electrons. But in the process, it also experienced a single replacement in which zinc replaced the hydrogen. And now the hydrogen is free to combine with other hydrogens and make hydrogen gas, the diatomic hydrogen gas. Okay. Combustion reactions. What do we mean by combustion? Combustion reactions are those which combine something with oxygen. Something over here combined with oxygen is a combustion reaction. Now, if we use this chart, this flow diagram, then we can subdivide reactions into precipitation reactions, oxidation reductions, and acid-base reactions. And the oxidation reduction reactions have a subgroup, the combustion reactions. The example that's given here is methane, CH4, combined with oxygen yields carbon dioxide and water. That is a combustion reaction. It's also an oxidation reduction reaction. It's a special case, yes. Synthesis reactions are those in which a compound is formed from simpler materials, very often from elements. Two elements combine to make a compound. But it could be simpler compounds, making a more complex compound. Here's an example. Carbon plus oxygen is carbon dioxide. It's also an oxidation reduction reaction. Notice that carbon is neutral on the reactant side, and it carries not a charge. All right, here's a simple rule. Let's say carbon solid makes carbon dioxide. Okay. Whenever you have an element on one side of the reaction equation, and you find it in a compound on the other side, and this works both ways. If it's element compounder or element compound, then you have undergone an oxidation reduction reaction without fail every time. Now, we can't assign charges to these materials because they're not ionic, but we can use a version, a bookkeeping scheme for tracking the movement of electrons. And what we have to do is assign oxidation states. So elements always have an oxidation state of 0. Compounds, we have rules for compounds. This is a covalent compound in which electrons are shared, so we don't have ions. But we say the oxidation state on oxygen is 2-. So that means we have a 4- total. That means this one must be a 4+ oxidation state. That way we can track the movement of electrons, right? If we go from 0 to 4+, we must have lost 4 electrons. Okay, that's how you use oxidation states. A decomposition reaction is essentially the opposite of a synthesis reaction. It's also oxidation reduction. Notice that we have compound on one side and its element on the other side. Excuse me. Okay, so now we can add some items to our flow diagram. So under oxidation reduction, we can have combustion reactions. We can also have synthesis reactions and decomposition reactions. All right. Can be classified as what kind of reaction? Well, one kind of reaction is a combustion because oxygen is there, elemental oxygen. But it's also a redox reaction. Oxidation reduction is often abbreviated as redox. Okay. It's also a synthesis. So all three are possible. Okay. All of these classifications apply to the reaction of hydrogen and oxygen to make water. Okay. So that's as far as we're going to go in this course with chemical reactions. So we've finished and we got a few minutes to spare. We've finished the chapter 6 and chapter 7 on chemical reactions. And we learned how to balance chemical reactions. We've learned how to predict some of the outcomes and how to write. We know what drives reactions. So let me stop the share. There we go. Let's see. Oh, that's okay. So what we'll do on Thursday is start a review process. And if we finish it on Thursday, then I'll show up the following Tuesday. Let's see. Hold on a second. Yeah, okay. Our exam on chapter 6 and 7 is Thursday, March 6th. That's when the exam. So we have a buffer day that I can use for anything, and I'll just start the review process. This coming Thursday, the 27th. And then if we finish it then, fine. If we don't, we'll continue the following Tuesday with review, and that'll lead up to Thursday exam. So I'll be zoomed in for both classes. And it just depends on how far we get as to what we'll be doing that day. If we finish the review on Thursday, then the following Tuesday, I'll just show up for half hour, 45 minutes to see if anybody zooms in with questions. Okay, that's it for today. And we're done.